Last up in this chapter is synthetic strategies. We're going to practice with trying to do all of these reactions together. Now, biggest thing that we can kind of think about in this chapter and what's new to add to our toolbox is that we have new carbon nucleophiles, and those carbon nucleophiles are super important in changing the carbon skeleton. So remember, these are the two questions that we want to ask ourselves when we are looking at a reagent or starting material and looking at how it's linked to the desired product. First step, is there a change in the carbon skeleton? Do we add or subtract things? And I really want to mention here that in all of these reactions that we learned in chapter 18, the carbon nucleophile ones, Grignard's, cyano groups, or the Wittig reaction, these all change the number of carbons in our group. So very, very important to remember those. And then the second question, is there a change in the functional group? Well, gosh darn it, I hope so. That's a synthesis, right? So these two reaction questions are should be at the forefront of our mind. The first one, new stuff, Grignard's, the cyano group, and the Wittig with the phosphorus ylide. We should be able to make a list of these products that can be made from aldehydes and ketones. I really highly recommend pausing to see if you can really come up with all of these lovely interconnections. We will practice them in class, obviously, but looking at carbon nucleophiles, hydrogen nucleophiles, nitrogen nucleophiles, sulfur nucleophiles, and oxygen nucleophiles, we have a variety of new reactions with our aldehydes and ketones that we can interconvert things from. Okay, so take that moment to go back and rewatch if you need to. Just to remind ourselves of spectroscopic analysis, things from chapter 14 and 15 are still really, really important for us, and you will still see them throughout all of our chapters in this semester. The carbonyl creates that strong C double bond O stretch around 1700. Remember, resonance provides less carbon-oxygen double bond character, and so usually we see a lower wave number for those carbonyl compounds that are conjugated. But again, aldehydes also give that weak peak around 2700 to 2800 centimeters to the -1 for the CH stretch. So really important to start thinking about what differentiates ketones and aldehydes in our IR spectrum. Here's just a good one to kind of remember. Not only for an aldehyde will you see the carbonyl peak, but you'll also still see the hydrogen of the aldehyde stretch around 28 to 2700. So that's what it would look like, just in case we forgot. Proton NMR is still important, right? So when we're thinking about a typical alkane, the methylene group, CH2 group, starts at around 1.2 ppm. Remember, when it's adjacent to a carbonyl, we add 1, right? Plus 1 ppm to appear more downfield for those methylene groups. So know the difference between the protons next to a carbonyl. Also, the aldehyde proton itself appears around 10 ppm. Carbonyl carbon produces a weak signal around 200 for the carbon-13 NMR. All right, so if we're thinking about carbon-13, again, yes, the adjacent carbons will be shifted more downfield that are right adjacent to our carbonyl, but the actual carbon of the carbonyl appears very far downfield at around 200 ppm. And here's our review of reactions, okay? So when we're looking at these reactions, we've learned quite a few this chapter. I would highly recommend concept mapping these and creating a chart for yourself so that you can do an overview of carbon, sulfur, nitrogen, hydrogen, and carbon nucleophiles.